All right, hello, this is the second video I'm making here. We have 6 more slides of questions. First one is, which of the following is the correct bond line structure for the chemical formula shown here? Now, I'm not going to be giving you condensed structural formulas on your tests. I really don't like them, but it might be a good skill to be able to read them and understand them, because you certainly will be given those on your ACS exam. All right, so what you can see are two things that we have in parentheses. Both of them are CH3s, and they've got subscripts after them. That means we have 2 methyl groups on the left side of the molecule and 3 methyl groups on the right side of the molecule. Those are being bonded to those carbons there. So what we want to do is find the terminal carbons, or maybe not terminal, but the ones next to it. And you can see right there is a carbon that has 3 methyl groups attached. We have that here, there, and there. If I were to, let's change the color of that one and make it red. All right, now that we can highlight that, that red one's going to be attached to 2 methyl groups. So we could see there's one with 2 methyl groups here, there, and that's it. The other carbons in the other structures are either bonded to 1 methyl group, or they have a group that's longer than a methyl group also attached. And then we have a single CH2 in between. All right, so really we can, at this point, cross out these molecules, and then you'll notice that molecule 2 has 1 group in the middle, 1 carbon in the middle, and so that'll be it. You should be able to count up your carbons too. You have 1, 2 from that, 1, 2, 3. All right, so there's whatever 2, there's 3, that's 5, 6, 7, 8. We've got 1, 2, 3, 4, 5, 6, 7, 8. This molecule 1 has 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, actually. So that would not be it. We could count 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. So if you did it just by counting, you could have eliminated molecule, actually not 4, you could eliminate 1 and 3. And then if you did it by, trying to connect the structures, molecule 4 did not have 2 methyl groups coming off of 1 carbon. So again, that gives you 2 as the correct answer. Second question, which of the following is the correct bond line structure for the one shown there? Kind of doing the same stuff here. So we have 2 of those are ethyl groups. So they're 2 carbons long, attached to this carbon here. So look for a carbon bonded to 2 groups of, let me change the colors of this. That carbon will be that one. It's bonded to 2 groups that are 2 carbons long, 2 ethyl groups, right there. So we've got that. You'll see molecule 3 does not have that situation. Neither does 4, and neither does 5. So just looking at that, and I'm picking arbitrarily. I'm not picking it just to make this question easier. That's just how I happened to look at it. There are certainly other ways you could do it, though. All right, the next is that this group that has CH2 in parentheses with a subscript 2 after it means that there are not substituents sticking out, but that is part of a linear chain, and that will actually be those 2. And you see that molecule 1 does not have that, so we now know that it's molecule 2. Being able to actually read that properly. But let's go further. We have a CH3. We have a CH that's also bonded to an oxygen. All right. And we can see there's a CH bonded to an oxygen. The H next to the O in the condensed formula is the hydrogen bonded to the oxygen in that alcohol. Next question, draw a bond line structure for that condensed formula. So this is not recognizing which one's correct, but actually utilizing it. So look for the functional group. There you have a triple bond. Just start with the triple bond. There's no reason not to. All right, every time you have a triple bond, it's going to be linear between the 4 atoms that surround it. And that'll be 1, 2, 3, and 4 there. No, actually, not that 4. One of those. There's 3 methylene groups, which are the CH2s. And so we have the one that's highlighted there on the right, 2 and 3. And then we're looking at that one will be the next carbon. And you see that one has 2 CH3s. So that's going to be like this. Then we have a CH2. Let me do that. That'll be to there. And then an OCH3. So we have an oxygen and then a CH3. But it's a bond line drawing, so we leave that out. So there you go. Let's count the carbons here. We've got 1, 2, 3. And then this 3 makes 4, 5, and 6, 7, 8, 9, 10, and 11 carbons. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And so there's your structure. I'll redraw it to make it less messy. Well, at least I'll try to. I'm not as good on this as I am on a chalkboard or anything, but I'll do my best. And if you want, you could put the lone pair on the oxygen. All right, next we have draw a bond line structure for each constitutional isomer with a molecular formula of C2H4O. So we have 2 carbons, 4 hydrogens, and an oxygen. All right, so I haven't shown this in class, but there's actually an equation we can use to calculate degrees of unsaturation, or just like how many double bonds there will be. It turns out like cyclic structures will also count as a double bond. So for example, in cyclohexane, it's C6H12, while the hexane itself is C6H14. If we have one hexene, this is C6H12, and so you can see cyclohexane and 1-hexene have the same chemical formula. So degrees of unsaturation will be including double and triple bonds and cyclic structures. So just keep that in mind. And so the degrees of unsaturation, I'm just going to put degrees of unsaturation, I don't know, du, equals 2 times the number of carbons plus 2 plus the number of hydrogens, or sorry, plus the number of nitrogens minus the number of hydrogens minus the number of halogens divided by 2. Notice oxygen is not in that equation. This molecule C2H4O does not have any halogens, and it does not have any nitrogens. So what we're going to get out of this is 2 times 2, because there's 2 carbons, plus 2 minus 4, because there's 4 hydrogens, and then we divide by 2. So you see 4 plus 2 minus 4 over 2, the 4's cancel out, and we get 1. That means we can have a double bond, or we'll have a cyclic structure. So what I would do is always start with the number of carbons and just make a linear chain of that. There's 2 carbons, so you have a line, and then there's an oxygen. All right, now you've got that. If we used fully saturated, there'd be 3 hydrogens there and 2 hydrogens there, and so this would have 6 total hydrogens. If we add a double bond, then there's going to be 1 hydrogen in the middle and 2 right there, and you can see that that has 4 hydrogens. So that degree of unsaturation equation works out beautifully. It does account for this structure, and really any that works. So we have a double bond between the two carbons there. We could also have a double bond to the oxygen. And now I'm going to draw the hydrogen in. We do that with this functional group. It's called an aldehyde, and we draw the hydrogens in for aldehydes just because it looks better. All right, so we have the double bond in either of those, and then, like I said, you can have cyclic structures. And when you have those three atoms together in a cyclic structure, you get this, which is called an epoxide. That's not in our functional group chart, but there you go. Each of these carbons has two hydrogens, and so it's C2H4O. All right, next we have draw a bond line structure for each constitutional isomer with molecular formula C4H11N. So for this, we have 2 times the number of carbons plus 2 plus nitrogen minus hydrogens, and then we don't need to include the halogens. So we get 8 plus 2, and we have obviously 1 nitrogen. All right, so you see here, that's going to be 11 minus 11 divided by 2, so we get 0 degrees of unsaturation. All right, so this molecule is going to have no double bonds, and it's not cyclical. So again, just start with 4 carbons, 2, 3, 4, and then attach your nitrogen to it. So go 1 more, add N, and nitrogen's always going to have 3 bonds. So just make it the simple one with 2 hydrogens, and there you go. We have 2 shown. There's going to be 2 more, 2 more, 2 more, and 3 more. So 3, 5, 7, 9, and 11. So that saturated form of this molecule has the proper chemical formula, matches the one given to us. All right, if we number it like this, we have the nitrogen bonded to carbon 4. Well, let's make that nitrogen bonded to carbon 3. All right, so 1, 2, 3, 4, and now we've got nitrogen here, NH2. All right, if we put the nitrogen on carbon 2, then that goes here, and it turns out that those are the same thing. So that's not adding anything new, and if we put it on carbon 1, it'd be the same as the one we had earlier. So having it outside of a linear structure like that, you get just those 2 options. Now, we could have 2 and 3 carbons, and then the nitrogen, kind of in the middle, and then a carbon there. So this is going to have 3 plus 3 is 6, 7, 9, and 11 hydrogens. So putting the nitrogen kind of within the middle of the chain, it doesn't affect the number of hydrogens that the molecule will have. And so this is another constitutional isomer that has that same chemical formula. All right, so I have the 3 carbons on the left, 1 on the right. If I do 2 carbons to the left and then the nitrogen, you could have this. Again, you can have 3 on the outside ones for 6, that one that's shown 7, and then the 2 ones here and there each have 2, so it has 11 hydrogens. All right, now we could also add on to that. Let's do 1 and 1, and then 2. Now we've got 3 plus 3 plus 3 is 9, plus 2 is 11. And so there you go. I would say those are the easy ones because the alkyl groups are all unbranched. We could also make branched versions of those. So like 1, 2, and 3 carbons, and then we have that there, and then we could attach a nitrogen like that. We could also have 1, 2, and 3. Oh wait, no, actually that one. let's see, 1, 2, 3, and then 4. So 4 is bonded to 2. 1, 2, 3, 4. 1, 2, 3, 4. There we go. Okay. 1, 2. You can see if I do this, the NH2 is bonded to 3. And although it looks different than that one, it's actually the same. All right, and then, so that was 3 carbons long. If we have 2 carbons long, we could have this structure right there. 1, 2, and 3, 4. All right, so those are the branched ones with the nitrogen with an NH2. If we have the nitrogen bonded to 2 carbons, all right, and it'll have to look like this, and then we could have the other 2 carbons there and there, and there you go. So 1, 2, let's go 3, 4. All right, so here we have the 8 constitutional isomers with the chemical formula C4H11N. There's no way to calculate the number that there will be. You just kind of got to draw them out. Having carbons and nitrogens makes it more complex than any other 2 elements. And next we have which of the following compounds both have a ketone and an ester. A ketone is any structure that has 2 R groups attached to a carbon-oxygen double bond. And an ester has an R group bonded to a carbon-oxygen double bond, but then there's an oxygen here and another R group. So if we look at the left molecule, 1 has a hydrogen there. That's an aldehyde. That's why, like, if you look at 1, it looks incomplete that way, to me at least. So that's why we usually put the hydrogen in. I would imagine whoever made this just wanted to leave it out to try to confuse students or conserve space. But we have an ester here, but there's an aldehyde right there. So not 1. 2 has the ketone here, but this is an ether. So because there's this carbon right there that's in between, this is not an ester, so that's wrong. In 3, we have a carboxylic acid and a ketone. There's a ketone, but because that's an acid, not an ester, 3 is incorrect. Same with 4. We have an alcohol and a carboxylic acid. This molecule 5 has an ester here, and this is a ketone, and so the correct answer is that one. Viricept, used in the treatment of HIV, has the following structure. Identify the functional groups in Viricept. All right, so we have, whoops, let's highlight that. That's an alcohol. I can spell, I promise. All right, we have this is an arene. Sometimes we could just say this whole thing there is a phenol. That's sometimes considered its own functional group. We have this right here being an amide. We have this right there being a sulfide. We have another arene here. Here's another amide. There's an alcohol. And then finally, wrong coloring apparatus, there we go. That is an amine. Draw the Lewis structure for the following compound. I don't really want to do this, but I will do it, I guess. I said in the class that you wouldn't have a question like this on a test, but there you go. All right. It just gets messy. Make sure every carbon has 4 bonds, every oxygen 2 bonds if it's neutral, every nitrogen 3 bonds if it's neutral. An oxygen that's negatively charged will have 1 bond. A nitrogen that's negatively charged will have 1 bond as well. No, I have 2 bonds. Sorry. An oxygen that's positively charged will have 3 bonds. A nitrogen that's positively charged will have 4 bonds. And then a carbon that's negative will have 3 bonds and a lone pair. A carbon that's positively charged will have 3 bonds and no lone pair. And that's what we get right there. All right, the bottom one, draw all the lone pairs of the electrons. All lone pairs of electrons for the following compound. So oxygens will have two bonds, 2 lone pairs. The reality is any atom, that's like carbon, oxygen, nitrogen, fluorine, whatever. If you have 4 lone pairs, you'll have no bonds. If you have 3 lone pairs, you'll have 1 bond. 2 lone pairs, 2 bonds. 1 lone pair, 3 bonds. No lone pairs, 4 bonds. And that will be true for any atom. And then if the atom is carbon, nitrogen, and oxygen, you have to use that information and how many valence electrons they normally would have to be neutral to figure out their formal charge. In this case, we have an oxygen that's got a formal charge of -1, so 1 bond, 3 lone pairs. The nitrogen there has a positive charge, so it will not have a lone pair because it has 3 hydrogens and 1 carbon bonded to it. And then the alcohol has 2 bonds to it, so 2 lone pairs. All right, the final page here. Which of the following is a Fisher projection? That will be this one. Which of the following is a Haworth projection? That is this one. We haven't actually talked about that in class. By the way, whoever wrote this forgot to put in... Oh, no, never mind. I just saw it. There's the 2. Okay. 2 is a Fisher projection. 3 is a Haworth projection. For the following compound, label the bonds that are out of the plane and behind the plane of the paper. These are out. Those are wedge bonds. And the other one said behind. Wedge bonds means in front of the screen or paper, and then dash bonds represent behind. And that is it for this assignment or this worksheet.